Hello everyone, I hope you guys are doing extremely well. Today we are going to discuss another problem in our binary search tree series. The problem name is search target node in binary search tree. So let us understand the problem description first. So we are given the root node of a binary search tree and we are given a target node and we want to search the target node in the binary search tree. So the problem statement is pretty clear. So let us take an example to understand it more clearly. So let us say we are given the root node of the binary search tree as 65. Now the left child of this node 65 is node 55 and the right child is node 75. Now the left child of node 55 is, let's say, node 45 and the right child is node 60. Now for node 60, let us say the left child is node 58 and the right child is node 62. And we want to search the target node, that is node 60, in this binary search tree. So as we can clearly see, this node 60 is present in this binary search tree here. So we'll simply return true, indicating that yes, this target node exists in our binary search tree. And if our target node is something like node 88, now we can clearly see in this entire binary search tree there is no target node, there is no node 88. So here we are simply going to return false. False will indicate that our target node is not present in the binary search tree. I hope the problem statement made sense to you guys. Now we are going to understand how we can solve this problem. So let us take an example. Let us say the root node given to us is node 55. Now the left child of this node 55 is, let's say, node 45 and the right child of this node 55 is, let's say, node 65. Now for node 45, let us say the left child is node 35 and the right child is node 48. Okay. Now for node 48, let us say the left child is node 46 and the right child is node 52. Now for node 65, the left child is null but the right child is node 77. Now we want to search the target node, that is node 46, in this binary search tree. So how can we do that? So we will start searching from the root node. So first of all, we will compare the root node and the target node. So root node is having a value 55 and target node is having a value 46. Now root node is greater than the target node. That means target node will be present in the left subtree because it is a binary search tree and all the values less than the current node will be present in the left subtree. So target node is less than the root node. Target node is less than node 55. That means this target node may or may not be present in the left subtree. So now we reached at node 45. Now for node 45, again we compare this node 45 with this target node, that is node 46. Now node 45 is less than the target node. That means this target node may or may not be present in the right subtree. So now we reached at node 48. Now on node 48, we again compare the node 48 and the target node. Now for node 48 and node 46, node 48 is greater than the node 46. That means node 46 may or may not lie in its left subtree. So now we reached at node 46. Now on node 46, we can clearly see this node 46 is equal to the target node. So from here we can simply return true, indicating that we have found the target node that we were looking for. So first of all, we compared with the root node and we checked whether the root node is having a value greater than the target node or not. If the root node is having a value greater than the target node, we will go to the left subtree. Why left subtree? Because the target node will be present in the left subtree only. So we reached at node 45. Now again we compared node 45 and node 46. node 46 was greater than node 45. So we deducted one thing, that okay, node 46 will be present in the right subtree. So we reached at node 48. We have done the same thing for node 48 and we reached on node 46. Now node 46 and node 46 are equal. That means we are simply going to return true from here. So from node 55 we reached on node 45. Now from node 45 we reached on node 48. From node 48 we reached on node 46, and simply we have returned true from here, and therefore the entire call has returned us true. Okay, so talking about the time complexity of this approach, the time complexity of this approach is big O of log n, where n is the number of nodes present in this binary search tree. Why big O of log n? Because at every point we are deleting an entire subtree. For the root node, we have considered the left subtree only. We have deleted all the nodes present in the right subtree. We don't need to check them. So at every stage we are eradicating entire subtree. So the time complexity is big O of log n, and the space complexity is big O of log n if we are using recursive code. That means if we are using recursion, so in recursion our stack is going to have at most n entries. So space complexity will be big O of log n in case of recursion, but in case of iteration it will be big O of 1. Now these time complexities and the space complexities are for average cases. What will be the time complexity and the space complexity for the worst case? Let me tell you what will be that. So if you remember the previous problem, insertion in a binary search tree, you know what I am talking about. So let us take a binary search tree having a node value 25. Now the left child of this node 25 is null and the right child is node 35. Now for node 35, the left child is null and the right child is node 45. Now for node 45, the left child is null and the right child is node 55. Now for node 55, the left child is null and the right child is node 65. Now let us say we want to find the target node, that is node 70. Okay, so first of all we are going to start from the root node and we are going to compare the root node and the target node. So node 25 is having a value less than the target node. That means target node will lie in the right subtree. So we will reach at node 35. Now for node 35, we will again compare node 35 and target node. Now node 35 is less than target node. That means target node will lie in the right subtree of node 35. So we reached at node 45. Now for node 45, we again check node 45 is less than the target node. That means target node will lie in the right subtree of node 45. So we reached on node 55. Now for node 55, we again compare it with target node. Node 55 is having a value less than the target node. That means target node will lie in the right subtree. So we reached at node 65. Now for node 65, we again compare this value with the target node. Now the target node is having a value node 70. So we reached at a null node now, because target node will lie in the right subtree. And now from here we reach to here, from here we reach to here, from 45 we reach to 55, from 55 we reach to 65, and from 65 we reach to null. Now from null we can go nowhere. So if we are getting this case, here we can simply return false. So here it will return false, then it will return false to its upper call, and so on and so forth. But what is the catch here? The catch here is we are comparing all the values of the nodes present in this binary search tree. So the time complexity of this is big O of n, where n is the number of nodes present in this binary search tree. And talking about the space complexity, the space complexity will also be big O of n if we are using recursion, and if we are using iteration, then it will be big O of 1. Okay, fine. This is the worst case. Why? Because this is nothing but a degenerate or a pathological tree. Okay, I hope the solution approach made sense to you guys. Now we are going to understand how we can code this. So in this video, I'm gonna code the recursive approach and I'm gonna give the iterative approach a homework to you guys. Please solve it by yourself. I'm gonna drop the iterative version code in the comment section, so do check as well. Okay, so let's do the code now. So as you can clearly see, I have already declared a function called search that is taking the root node and the target node as an argument. Now the root node and the target node are nothing but the objects of class tree node. A class tree node is having a constructor that is initializing the value of the node and then initializing the left and the right subtree of a node as null by default. Okay, now in this function what we need to do, the first thing that we need to check that if the node that I'm currently on, that is if root is null, from here we need to return false. Why? Because we haven't found our target node, so we need to return false. What is the second case? The second case is if my root dot value is equal to target node dot value. So here, from here we need to return true, that we have found this target node that we were looking for. Okay, now what is the other thing? The other thing is if my root dot value is greater than the target node dot value. So if this is the case, that means our target node will lie in the left subtree, because the root node is greater. That means target node will lie in the left subtree. So we'll make a call for the left subtree. So return search, and then we'll pass root dot left and then the target node. Now else means the root dot value will be less than the target node dot value. So our target node will lie in the right subtree. So now we are going to make a call for the right subtree. So return search root dot right and then target node. And that's it. That's all about our code. So let us take a very quick example to run our code. So let us say the root node is nothing but node 15. The left child is having a value of 10, and the right child is having a value 25. Okay, now let us say the left of is nothing but 2. Okay, that now let us say the target node is we were looking for, let's say 2, and let us take one more target node. Let's call it target node 1, and that target node is having a value 26, which is not present in our binary search tree. So let's call search function for both the target nodes. So root and then target node, and then again call this function print search and then root comma target node 1. Let's give our function a run to check the output. So the output of the code is coming out to be true and false. True is coming out for tree node 2 because tree node 2 is present in our binary search tree, and false is coming out for tree node 26 because 26 is not present in our binary search tree. Let me draw the structure of the tree as well. So the tree that I have taken is 15 is the root node, 10 is the left child of 15, 25, I guess 25 or 26 is the right child of 15, and 2 is the left child. Now we were looking for node values 2 and 28, I guess. So as we can clearly see, this 2 is present in this binary search tree, so it returned us true, and 28 is not present in the binary search tree, so it returned us false. I hope the code made sense to you guys. Now, if you guys still have any queries regarding this problem, please drop your concern in the comment section and I will be more than happy to help you there. Regarding the series, I will be uploading more of the questions in the upcoming week, so keep following us. Until then, keep smiling and keep coding. Thank you.